Hello, welcome again. We are solving some questions of fluid mechanics and machinery. The topic is hydraulic machine. Question number 29 is the internal and external diameter of an outward flow reaction turbine are 2 meter and 2.75 meter respectively. The turbine is running at 250 rpm and the rate of flow of water through the turbine is 5 meter cube per second. The width of the runner the width of the runner is constant at inlet and outlet and is equal to 250 mm. The head on the turbine is 150 meter. Neglect the thickness of vanes and taking radial discharge at outlet. The vanes angle at inlet and outlet are option A, inlet angle 6.072 degree, outlet angle uh, 2.512 degree. Option B, inlet angle 6.072 degree, outlet angle 3.68 degree. Option C, inlet angle 5.132 degree, outlet angle 2.512 degree. Option D, inlet angle 5.132 degree, outlet angle 3.68 degree. Okay, so the internal diameter is 2 meter and external diameter is 2.75 meter, and speed of turbine is 250 rpm and the charge is 5 meter cube per second. So width of inlet and outlet, width at inlet and outlet are equal, that is B1 and B2, that is 250 mm or 0.25 meter. So head is 150 meter. So discharge at outlet is radial. So it means dW2 is 0. So there is a radial discharge, it means there is no work component of velocity. So that is Vf2 is equal to V2. So absolute velocity is only that Vf2. And tangential velocity of that turbine at inlet and outlet are inlet corresponding to inner and outer diameter respectively, because this is outward flow reaction turbine. So U1 will be corresponding to 2 meter and U2 will be corresponding to 2.75 meter. So U1 is your 26.18 meter per second and U2 is your 36 meter per second. Okay. So the discharge through turbine is Q is equal to pi d1 v1 vf1 is equal to pi d2 b2 vf2. Okay, and vf1 is Q by pi d1 v1 from this. Okay, and d1 is known, v1 is known, and Q is also known, that is 5. So vf1 and vf2 can be calculated. So vf1 is your 3.18 3 meter per second and Vf2 is 2.315 meter per second. Vf1 and Vf2 are flow component of velocity. Okay. So now from energy balance we have water power available at inlet, that is rho Qdh should be equal to water power that is used and that water power that is unused. So power that is used is power drawn by turbine, that is rho Q Vw1 U1, because Vw2 is 0, discharge is radial, so the power drawn by turbine will be only rho Q Vw1 U1. Actually it is rho Q Vw1 U1 plus Vw2 U2, but Vw2 is 0, so it is only rho Q Vw1 U1. And the power that is unused is expressed in terms of kinetic energy per second. So that is rho Q V2 square by 2. That is the V2 is the absolute exit velocity of water. Okay. Now we have V2. V2 is your Vf2, because at exit there is only the radial exit. So V2 is your V2 is your 2.315 meter per second, and H is your 150 meter, and U1 is 26.18 meter per second. Okay. So V2 H and this U1. Okay. Uh, so this is your radial discharge. This is H. Okay. So from this we can calculate. Because the only unknown thing is now because rho Q will cancel out, and here it will be GH, and here will be Vw1 U1, and here will be V2 square by 2. So only unknown thing is your Vw1. So from this we can calculate Vw1. So Vw1 comes out as because we have U1, we have V2, we have H. So Vw1 is your 56.1 meter per second. Now consider inlet velocity. So this is your absolute velocity, and this is your relative velocity, and this is the blade velocity at inlet, and this is the work component of velocity, and this is the flow component of velocity. And as this is work component and this is blade velocity, so this will represent horizontal relative velocity, and this will represent vertical relative velocity also, because there is no vertical or no no velocity of blades in the direction of flow. So it is also representing relative velocity. So that is the total relative velocity. Okay. So this is the inlet velocity diagram, and from this diagram we have tangent theta, that is blade angle at inlet, is Vf1 by Vw1 minus U1. Okay, now we have Vf1, we have your Vw1, and we have U1. So from this we can calculate theta is your 6.072 degree. So this is the inlet blade angle. And now the considering outlet velocity diagram, because the charge is radial, so this is your V2 and this is your U2. Okay, so this will be your VR2. Okay, so VR2, and this will be and this will be your blade angle VF2 by U2. Okay, so this will be so pi will be your 3.68 degree. Okay, so here the direction of arrow can be drawn downward, or this direction can be taken here. To make it relative velocity. So answer is 3.68. Okay, so answer is 3.68. This velocity and this angle and this angle.